Hello, Math 201. Welcome to today's lecture on section 4.7, L'Hopital's rule. And so real quick, I just want to make a note on how you pronounce it. It's pronounced L'Hopitals, not La Hospital, which a lot of times when people see that, they think La, and then that S kind of dyslexically gets placed right there, and we call it La Hospital. That's kind of a fun way to remember it, but it's L'Hopital. That's how you pronounce it, L'Hopital. From now on, I'm just going to do L apostrophe capital H. So that means L'Hopital, and it's going to be a rule we use in evaluating limits. And so what L'Hopital does is it allows us to calculate limits that are in indeterminate form. So 0 over 0 or infinity over infinity. And so you'll remember from before that when we had 0, 0 or infinity over infinity, we had to do something special, either some algebraic trick or something like this, where we had to use geometry and kind of a lot of really interesting stuff to get this limit. Generally, remember when we try and do a limit, you just try plugging it in. And if you plug it in, you get sine of 0 over 0, which is 0, 0, so it's indeterminate. We know what this limit is. We know it's 1 because we proved it using kind of like triangles and stuff. We did that. But we are going to prove today a much easier way to do that. And so an indeterminate form can take on any value. So we have to be careful. When it says 0 over 0, we have no idea what that means. Like this limit could be anything. This one in particular is equal to 1. But there are other limits of the form 0 over 0. For instance, the limit as x approaches, I don't know, if you did like x squared over 2x squared, that limit is 1/2 as you go to 0. And so it depends. And so you have to be very careful. These are indeterminate. They can be anything. And so here's an example to show you that it could be anything. Limit as x goes to infinity of ax over x plus 1, where a is a constant. If you try plugging it in, you get 0, or you get infinity over infinity, right? Infinity, infinity, so it's indeterminate. But we know what this limit is, right? By pulling out this a and then taking this limit right here, which is 1, then you get a times 1 is equal to a. So infinity over infinity could literally be anything because a is any constant. And so whenever you have infinity over infinity when you plug in, or 0 over 0 when you plug in, you just have to be careful because it can really be anything. And so indeterminate forms, we can use algebra to manipulate and solve, but some we can't, right? So L'Hopital's rule is a tool that helps us calculate indeterminate form limits where we don't have the ability to do algebra like this. And so here's the theorem. And so this is L'Hopital's rule technically for 0 over 0. So if f and g are two functions, differentiable on some intervals, that means they're just nice functions. And we have that the derivative of g is not 0 at a. Then what, and we have that both those limits are going to 0. So sorry, the derivative is not 0. So the derivative of g prime can't be 0 because then this limit wouldn't exist. So the limit so if these things are both going to 0, those limits, then you can take the limit of their quotient. So if this quotient gives you 0, like when you plug in, you get 0 over 0. Instead of taking this limit, you can take the limit of the derivatives. So this is not the quotient rule. This is saying take the derivative of the top. It's what you wish the quotient rule was. It's take the derivative of the top, divide by the derivative of the bottom, and then take the limit. And if this limit exists, then it's the same as the original limit. And so this allows us to find things like sine of x over x. The proof is actually really easy. And so I'll just do it real quick and I'll just kind of do the sketch. But the idea is this. This proof, this limit right here, is the limit as x approaches a of f prime of x, g prime of x. That's just f prime over g prime of a because f prime and g prime are continuous. So you can just plug it in. And because g prime of a is never 0, you can just plug it in. It's totally fine. Then what happens is the limit as x approaches a of the top, that's the definition of the limit. And then this is, or the definition of the derivative, that's the definition of the derivative down there. And then what we can do is we can pull out the limit because this is just a quotient of two things. And then you have f of x minus f of a over x minus a, g of x minus g of a over x minus a. But then since x minus a is not 0, that cancels out with that. Those two things cancel out. And so we get f of x minus f of a over g of x minus g of a. And then we can just actually separate this into two things. So it becomes the limit as x goes to a of f of x over g of x. That's because f of a and g of a were both 0, right? If you actually plug in a to the function, it has to be 0 there. And so it's just equal to the limit. And so that's the idea. And so it's not a crazy proof, but it's probably easiest to show how L'Hopital's works in action. So let's do it. So use L'Hopital's rule to evaluate the following limit. So if you try plugging in, what happens? Plugging in, we get the following. We get 1 plus 1 minus 2 over 1 minus 1, which equals 0 over 0. So indeterminate. Indeterminate. So L'Hopital's rule. So this is how I would like you to write it. So L'Hopital's rule, what does that give us? It becomes the limit as x approaches 1. And then it's the derivative of the top. So 3x squared plus 2x minus 2 over the derivative of the bottom, which is 1. And so this is the new limit. And what does that limit equal? Well, that one we can just plug in and you get 3 plus 2 minus 2 all over 1. And so that equals 3. And so that means the limit is 3. Because all we did is we took the derivative of the top over the derivative of the bottom and then evaluated that limit. And that limit was 3. And so that means this original limit is 3. So maybe I should write that. Whoops. Copy, paste. So that's how you do it. Let's try this one. Copy that guy, paste them. So if we plug in, what do we get? We get square root of 9 minus 3 over 0, which equals 0 over 0, indeterminate. And so L'Hopital's rule, what does that give us? The derivative of that is 9 plus 3x to the negative, so it's 1/2, to the negative 1/2 times 3 all over the derivative of that, which is 1. And this needs to be the limit. Oops. We should be taking the limit as x approaches 0. So now when you plug in 0, this becomes 1/2 9 to the negative 1/2 times 3. And so that is equal to, what is that equal to? 9 to the negative 1/2 is going to be 1 over 3. And so this is just actually going to equal 1/2. So that's our limit. Our limit is just 1/2. And so that's L'Hopital's rule, right? So whenever you get an indeterminate of 0 over 0 or an infinity over, I guess we'll talk about infinity over infinity next. But whenever you get 0 over 0, you can use L'Hopital's rule to take the derivative of the top and the bottom. So that's the derivative of the top, this is the derivative of the bottom, and then you can evaluate the limit. And so we get 1/2. So what happens when L'Hopital's rule fails? What if it's still indeterminate? So let's check that out. So this plugging in, excuse me, plugging in, we get 1 minus 0 minus 1 over 0, which equals 0 over 0. So this is indeterminate. So let's use L'Hopital's rule. L'Hopital's rule gives us e to the x minus 1 over 2x, the limit as x goes to 0. But plug in, you get 1 minus 1 over 0, which equals 0 over 0. So it's indeterminate again. And so what we can do is we can take L'Hopital's again. So we can do L'Hopital's rule twice. Whenever you get an indeterminate form, you can just keep doing L'Hopital's rule. And so we take the derivative of the top and bottom again, and this becomes e to the x over 2. And that one we can't evaluate, that becomes 1 over 2. And so that is the limit. So that's equal to this guy right here. So that limit is what we want. So this one was an example where we can use L'Hopital's rule twice. All right. Now we'll talk about L'Hopital's rule for infinity over infinity. It's the exact same thing. Basically, if you try plugging it in and you get infinity over infinity, you should take the derivative of the top and bottom and try again. So let's do this. So the limit Let me save myself some time. So plug in, and you get infinity over infinity. And so let's do L'Hopital's rule. So L'Hopital's rule gives us 12x squared, the limit as x goes to infinity of 12x squared minus 12x all over, let's see, 12, no, 6x squared minus 10. And so if you try plugging in, so plug in, you'll get infinity over infinity again. And so then you can do L'Hopital's again. We get the limit as x approaches infinity of 24x minus 12 over 12x, which plug in, you get infinity over infinity again. And so we can use L'Hopital's rule a third time, and we get the limit as x approaches infinity of 24 over 12, which equals 2. And so that's the limit. And so that's using, so obviously this is using L'Hopital's rule 3 times, and so it's not the most efficient way. We know from old techniques, right, that limit's just 2 because you take the ratio of that over that. Now let's try this one. This one's actually pretty interesting. So let me copy that. Oh, it's already copied. Let me bring it up here. So for this one, if you try plugging in, so plug in. So if you plug in, what happens is you get ln of 0 over cosecant of 0. ln of 0 is negative infinity. Cosecant of 0, so cosecant is 1 over sine, so 1 over sine of 0. And so sine of 0 is 0, and so this is going to be negative infinity over infinity, which is indeterminate. We don't know what that is. And so we'll use L'Hopital's rule. So by L'Hopital's rule, we get that this is 1 over x, and then the derivative of cosecant x is cosecant x negative cotangent x. And it's technically, sorry, it's the limit of this. I get on people who, whoops, I get on people who don't write the limits, and I'm not doing it myself. 0 from the right. Okay, and so we can try plugging in. So plug in. If you try plugging in 0, you get 1 over 0, and then you get negative 1 over sine of 0, because cosecant is 1 over sine, and then cotangent is cosine over sine, so cosine of 0 over sine of 0. And so what does that equal? That'll be infinity over, and then what is this going to be? This will be infinity and then times, so I guess it's 1 over infinity, or it's 1 over 0. And so that's going to be, because this is 1 over 0, this is also 1 over 0. And so it's 1 over 0 times 1 over 0. And so it's also going to be, so it's going to end up being negative 1 over 0 times 1 over 0. And so that's equal to infinity over negative infinity. And so this is also indeterminate. And so we would think that, okay, we have to do L'Hopital's rule again. But actually, L'Hopital's rule is going to make this kind of complicated, because that's going to get more complicated, and that will get more complicated. And so there's actually a clever trick we can do here. The fact is that cosecant and cotangent can be brought up top. And so we can use a little algebra. So use clever algebra instead. Because, and the reason why we would want to do this is because L'Hopital's rule on this would kind of make things more gross. And so using some clever algebra, I can rewrite this as the limit as x approaches 0 from the right of 1 over x, and then bringing these guys up top becomes times negative sine x, negative sine of x, and then tangent of x by bringing those guys up top. So all I did is I brought these guys up to the top. And now this right here is a limit I know, right? 1 over sine of x over x. So this becomes the limit as x approaches 0 from the right of negative, or let me put the negative on the outside with the tangent of sine of x over x times negative tangent of x, right? And this limit right here, we know, and then this limit right here we can do. And so just using the limit laws, just break this up into two limits. The limit as x approaches 0 of sine of x over x times the limit as x approaches 0 from the right of negative tangent of x. And now we can take those limits separately. This limit is 1, right? The limit of sine of x over x. And then the limit of negative tangent of x, well, tangent of x is just sine of x over cosine of x. And so it's 0 over 1. And so this is 0 over 1, which equals 0. And so that's the limit. So the final limit, so that limit right there is equal to 0 by doing L'Hopital's rule and then doing some clever algebra to leverage that limit, which we know, the limit of sine of x over x. Okay, let's talk about two more indeterminate forms. So 0 times infinity and infinity minus infinity. So these are indeterminate because when you try and evaluate that, we don't know what's going to win, 0 or infinity, and we don't know what's going to win here. Is that infinity bigger or is that infinity bigger? And so when we have 0 times infinity, we have to do some special stuff. Oh, I meant to erase this. Well, since I have it here, let's just go through it. So the idea for when you have a 0 times infinity, so for instance, x squared times sine of 1 over 4x squared, you want to rewrite it in terms of either 0 over 0 or infinity over infinity. Because if you try plugging in infinity, you'll get infinity times sine of 1 over infinity, which is infinity times sine of 0, right? 1 over infinity is 0. That's infinity times 0. This is an indeterminate form. And so we need to rewrite in a form where it's 0 over 0. And the way we do that is we bring this guy down to the bottom. And so it becomes sine of 1/4 x to the minus 2, and then x to the minus 2. And if you plug that in, you get sine of 0 over 1 over infinity, which is 0 and 0 indeterminate. Now we can use L'Hopital's rule. So by L'Hopital's rule, this is equal to x, the limit, and then the derivative of this is by chain rule, cosine, leave that alone, and then times the derivative of that guy, which is you bring the -2 down and you get -1/2, and then x to the minus 3. The derivative of this guy is just -2 x to the minus 3. And so we have an x to the minus 3 here and x to the minus 3 here, and they cancel. And so that's really nice. And then we get the limit as x goes infinity cosine of 1 over 4x squared. So just bring the x to the minus 2 down here. And then times -1/2 -2. Well, those guys just simplify to become 1/4. And then I can plug in infinity right here. And so I get cosine of 1 over infinity, which is cosine of 0. And so you get cosine of 0 times 1/4, which equals 1/4. And so the final limit is just 1/4. And so this is an example of where L'Hopital's, where you have to rewrite it to get it into L'Hopital's form. And so that's something that will happen. And so here's another one where we have to rewrite it. And so if we just try and evaluate it, so if we just try and evaluate, so just plug in. If you just try plugging in, you'll get infinity minus square root of infinity squared minus infinity. But obviously this one is bigger than that one. Infinity squared is bigger than infinity. This whole thing's going to infinity. And so this is infinity minus infinity. So this is indeterminate. We don't know which one's going to win. And so how can we write this in a form that will, that we can use L'Hopital's on? So what we're going to want to do is we're going to want to have something that we can pull out of both of those terms to get it to be infinity times something, and then rearrange that so we can get into L'Hopital's form. And so this is kind of be some clever kind of algebra again, but if you've kind of seen them a couple times, you get kind of used to it. And so it's x minus, and what I'm going to do here is because I need to pull out something from that term and that term. The only thing I can pull out here from is an x. So I need a way to get an x out of here under the square root. And so I need to pull out an x squared. If I pull out an x squared, what's left is 1 minus 3. And then pulling out an x squared from here leaves me with an x to the minus 1, right? Because if you distribute that to that and that, that will give you that. And so that's what we're going to do. Then the square root of x squared, because we're going to infinity, this is just x. And so I can pull that out and pull that out. And so what's left over is the limit as x goes to infinity. As x goes to infinity, because the square root of x squared is just equal to x when x is greater than 0. And so what this is equal to is x, and then pulling that out, I get 1 minus, and then the square root of 1 minus 3x to the minus 1. So that's what's left over. And now plug in. So plug in. And what do I get? I get infinity times 1 minus square root of 1 minus 3 over infinity, which is infinity times 0. Infinity times 0, which is an indeterminate form. Whoops. So indeterminate. And so in order to get into L'Hopital's form, I'm going to put this 1 over x on the bottom. And so this becomes the limit as x approaches infinity of 1 minus the square root of 1 minus 3x to the minus 1 over x to the minus 1. If you plug in that, this becomes plug in, you get 1 minus, this will be square root of 1 minus 0 over 1 over infinity, which is 0. And so it becomes 0 over 0 indeterminate, right? Because 1 minus 1 over 0, so it's 0 over 0. So by L'Hopital's, so by LH, what is this equal to? This is going to be equal to the derivative of this guy is 1/2, and then thing on the inside, 1 minus 3x to the negative 1, times the derivative of the inside, which is going to be positive 3x to the negative 2. And then the derivative on the bottom is negative x to the minus 2. The limit as x goes to infinity. The nice thing here is that that will cancel with that. And so we're going to get something hopefully pretty straightforward. So this becomes the limit as x approaches infinity of 1/2 1 minus 3x to negative 1 times 3 all over negative 1. If we plug in infinity into that, this will become 0. So that's going to 0 because negative 3 over infinity is 0. And so we get 1/2 times 3 over negative 1. So it's negative 3/2. So that's equal to our limit. So our limit is that. And we're done. And so this one's probably the most difficult algebraic one. But whenever you get infinity minus infinity, that's the trick. There's something that you need to be able to pull out of both terms in order to get it into 0 over 0 or infinity over infinity. All right, let's talk about one last kind of indeterminate form. And so whenever we have limits of a function raised to a function, so exponential functions, the idea is that if that limit were to exist, then doing our little ELN trick of both sides, this right here can be remanipulated. This g of x can come down in front, and then ln of x, but then this limit by limit laws can just actually pull out. And so you get e raised to the limit of this thing is equal to that, because those things cancel out. And so therefore, if this limit right here, if that goes to L, so if this is L, then that means P, your original limit, is just equal to e to the L. And so that's why in order to determine what this limit is, we instead look at this limit, and whatever that limit is you raise e to that, and that will be our limit. And so that's whenever we get indeterminate forms of 1 over infinity, 0 over 0, or infinity to 0. These are all indeterminate because 1 to infinity, we don't know if that's going to go to infinity or if that's going to go to 1. And then 0 to 0, we don't know because anything raised to the 0 power is 1, but 0 is 0. And so we don't know if that's 0 or 1. And then infinity to the 0, we don't know if that's going to go be really big or if it's going to go to 1. And so these are all indeterminate. They don't make sense as written. And so you need to reevaluate them. And so let's do an example. So the limit as x approaches 0 from the right of x raised to the x. So if you try plug in, what happens is you get 0 to the 0. This is indeterminate. And so what we're going to do is we're instead going to look at this limit, the limit. So analyze, so look at the limit as x approaches 0 to the right, and then take the natural log. And so it's x times ln of x. So instead we look at this limit, which this limit is going to equal, if you plug in 0, this is going to be, so if you plug in, this is 0 times negative infinity. So this is indeterminate. And so, but it's not in L'Hopital's form, and so we need to rewrite it, but that's not hard. So rewrite, and you get the following. It's limit as x approaches 0 from the right, and it'll be ln of x over x to the negative 1. But that, so plugging in, that's negative infinity over infinity. And so that's indeterminate form that we can use L'Hopital's rule on. So by L'Hopital's rule, that is equal to the limit as x approaches 0 from the right of 1 over x, and then negative x to the negative 2. But then that is just equal to the limit. That's going to cancel with one of those. So maybe I won't write it like that. Let me just rewrite. So bring this x to the minus 2 back up top. This becomes, the limit as x approaches 0 from the right, 1 over x times negative x squared, which equals negative limit as x approaches 0 from the right of negative x, which equals 0. And so that means that the limit as x approaches 0 of our original thing, x to the x, is just e raised to whatever this limit is. So this gets plugged in right here. So e to the 0, and so this equals 1. And so the limit is, as we go to 0 of x to the x, is just 1. Because you can't actually plug in 0, right? If you try plugging in 0 into that, 0 over 0 doesn't make sense, but it's going to get really, really close to 1 if you plug in numbers really, really close to 0. Okay, let's do one final example and then call it a day. So again, same issue. If you plug in, you'll get 1 plus 0 to the infinity, which is 1 to the infinity indeterminate. And so look at the ln. So take the natural log. So taking the natural log, it's the limit as x approaches infinity. So g of x, the exponential is x, and then natural log of 1 plus 1 over x. And I'm going to rewrite this because I know that that's going to go to infinity, and this is going to go to 0 because it's going to be ln of 1. So I'm going to rewrite this as limit as x approaches 0 of ln of 1 plus 1 over x, and then x to the minus 1. And then that, if you plug in is 0 over 0 indeterminate. And so this by L'Hopital's. So by L'Hopital's rule, we can take the derivative. This becomes 1 plus 1 over x to the negative 1 times the derivative of that, which is negative x to the negative 2. And then this is negative x to the negative 2, limit as x goes to infinity. So that's nice. That will cancel with that. And so this equals the limit. If you plug in infinity, you get 1 plus 0 to the negative 1, which what does that equal? That's just 1. And so that means the limit of when you take the natural log of this thing, so the natural log is 1. And so that means the original limit is just e to that. Oops. So that means the original limit, paste, is equal to e raised to whatever our ln limit was. 1. So it's e. So this is actually a really important limit. The limit as x approaches infinity of 1 plus 1 over x to the x equals e. This is a very, very important limit. And it's actually a way to define what e is. All right, we'll call it there.